Hello and welcome to another installment. Hopefully, sorry about the late delay, late start. Sorry. Okay. Um, so where we left off, we were running the our test code, trying to get things to work on Vivado, which we will now start. My computer crashed, so I'm a little late in setting everything up. Sorry about that. And when we run the simulation, we get the test code running until the verification tells us we stopped at cycle 115. Now, I've been kind of busy while we were away. And one of the things I did was actually two things I did. So let's update the project. We have unchecked changes. Okay. So first of all, I'm simulating the scene flag, which means that we can now check whether this is a new command even when we're executing from a real CPU, which means that our test plan now is much cleaner, because if we look at the test plan, it now has these lines with the comments only for bus cycles where we're actually fetching an opcode. So it's now much easier to find out where we are in the code. So if it says that we ran up to cycle 115, we can now go to line 115 and then go up to the first line that has a comment, and that's the opcode we're failing on. So that's one big difference, and hopefully it will be simpler now to check to get things working, to find out where we are. The other thing, let's just rerun the simulation. Right. Okay. So with that, let's load the test program from which we're working. So that was in test harness test program.s, and we were at LDA 0 page test. We're at this line. So opcode A5 is not implemented. What is opcode A5? You ask yourself, right? You're asking yourself. Opcode A5 is, well, we saw it over there. It's load A from 0 page. That's A5. So, time to do that. As before, we're loading the decoder. Let's just go into the correct directory. We're loading the decoder, and we want the case for all the opcodes. So we're looking for A5, and we want to handle ADDR mode 0 page and handle op LDA. So in theory, that's it. We're done, right? Except handle ADDR 0 page is not implemented. So let's go and implement that and understand how addressing modes work. So first of all, just as a reminder, LDA, the what we're doing inside the what we're doing inside the what we're doing inside the op handling is we're looking at the instruction counter, and by this point, the part of the address resolution of the addressing mode was supposed to have the correct address loaded on the bus. So we can. So if we look at the instruction counter register, it's an enum that contains the two fetch cycles, and then address fetch cycles, which I thought 11 would be enough, and the command cycles. So those are the cycles we go through. I have no idea what pending is. I don't think I'm using it. Just a second. I'm just curious. Yeah, not using it. Okay. So that's the op part. And as a reminder, if we look at A9, it does handle ADDR immediate and then handle op LDA. So the same op gets handled, but the ADDR part is different. So if we look at the ADDR part for immediate, we see that it takes care to do the loading part, and then it makes sure that the next instruction counter is op1, which brings us into the handling the actual operator. So if we want to add support for 0 page, what we need to do is implement this part. And again, our guideline is the test plan. The test plan tells us that, okay, we fetch from 030B the load A instruction itself, and then we fetch from 030C, which is automatic. I'll remind you, the 6502 second cycle always fetches from the program counter +1. Always. Doesn't matter what it is, but typically that's what we need, because in this case, it contains A9, which is the address to fetch the actual operand from, and indeed the next one fetches A9. So, what we want to do is probably duplicate this. ADDR immediate, absolute, and that's all we have right now. So let's add 0 page. And we're active only if we are in the address part of the instruction counter. And we say, okay, ADDR1, we want to advance the PC. Why? We don't need to fetch. The fetch instruction already took care of that. But we did consume this address, right? So we want the next instruction from read from 030D. So we do need to say that, because for there are addressing modes where we did not consume the address. We just read it because we have to. And in those, we don't want to advance the PC. So we want to advance the PC. And at this point, nothing else. And then at C ADDR2, we are going to get on the bus the address that we actually read here. So this A9 that came here, right now we're going to see it in the, wait for it, we're going to see it in the data latch. Let's check that that's indeed the case, because I'm making assumptions here. So let's make sure they're correct. Reset the simulation. And run. Okay, and now if we look at the instruction counter at CADDR3, we see that the DL has A9. In fact, it already has it at ADDR2. Let's go back to the code and see why. Sorry, ADDR2, right. So at ADDR2, DL has A9. What do we want to do with that? What we want to do with that is, if we look at the block diagrams, the address bus, what goes out on the address bus, comes from these two registers, the address bus high register and the address bus low register. Now those are actual latches. They output the value on the same cycle that I tell them to load, because otherwise everything would take an extra cycle and I just didn't want to do that. So what we want to do is we want the address bus low, the ADL, to have what the data latch had. So we need LDL ADL. So control signals O, CTL, DL ADL, set it to 1. Just as a reminder, the way constants in system Verilog and Verilog work is the number says how many bits there are, and then a tag, and then a character that says what base it is, B for binary, and then the actual value. So 1 tag B1 is a 1-bit literal. So we set that to 1, and that should put this A9 on ADL, which I lost here. It's somewhere here. ADL, instruction bus. Just a second. We don't have ADL? No way. Data bus source, data bus, special bus source, special bus, ALU, here we go. Address bus low. So address bus low is, source is ADL invalid, and ADL itself is X's, obviously. And now if I recompile and rerun, we should get that on ADDR2. Address bus low is still, right. Okay, my bad. This is not in the document we're working with is for this original 6502. We're doing an FPGA implementation, so buses are not just shared wires where everybody push whatever they want. They are multiplexers, which we need to set the source. So while this value exists, the correct way to use it is to say ADL source is CTL. 2 weeks and I forgot everything. Right. And now, if we run, we are on CADDR2, and address bus low source is DLADL, and address bus low is A9, just like we want. At this point, we can set the ADL-ABL control bit, and that will latch it on the address bus low. So, control signals CTL, ADL, ABL is 1. And now, if we reload, ADDR2, and we are supposed to see the CPU request address. The high value is 03 because that's what it was before, but the low value is A9 because that's what came from the DL, from the data latch. Okay, so low part handled. Now we need to handle the high part. Now the high part originally had these open drain MOSFETs, which were used to produce zeros. The default for this, everything is TTL logic here. So the default is 1. That's the pre-charge MOSFETs. You see, they have no control lines. They just output 1 if they only can. And this is controlled, connected to ground, and that produces either a 0 on the 0 bit or a 0 on bits 1 through 7. We want everything to be 0 because we want to produce a 0. So we want to set both ADH0 and ADH17. So control signals ADH. O to ADH0. So output 0 on ADH0 and output 0 on ADH17. But because we're not working with a bus, because we're working with a multiplexer, that's not enough. We also need to say ADH source is, and I forgot how it was called, so let's look it up. Source, ADH source, that's called the Gen ADH. So that's the generator. Okay, I've got a question about what board I'm targeting. This is not targeting any specific board. I did load it with the board I'm using, which is some QM-Tech Spartan 7, which is now long out of circulation. But the project itself is supposed to be integrated into CompuSAR. And the whole point here is that we're building a 6502, which is different than the normal way a 6502 works. I had a whole video about it, explaining why we're using synchronous and why we don't care about cycles. We're not issuing a bus, and only the buses need to be compatible. I have a whole video about it, which you're welcome to watch. You probably got to the channel through that video anyway. But so this project is meant to be integrated into another project. That being said, it's currently configured for the Spartan 715 or something like that, because that's what I have. Okay, so back to the code. We used the generator and we told the generator to generate zeros, all zeros. So that should give us zeros in the ADH. So ADDR2 and ADDR bus high is 0. And what we still need to do is to load that into the latch. And we can do that similar to here. So that ADH, ABH. And if we rerun, on ADDR2, we get that the address is 00A9. Cool. So we need to do one more thing. We need to tell it to actually perform a read. So like I said, this is a synchronous bus, and it doesn't perform a read automatically. We need to tell it that the request is valid. So we need to set CPU rec. That's not how it's called. It's called bus rec valid. We set it to 1. And by default, everything is set to read, but we'll double check. So 1 bit 0. This is a 0. Remember, 1-bit binary 0. And that should perform the bus operation, and which means we should get to 116 at this point. Right, 116. And we see that we did the bus operation. And there's one more thing to do, because at this point, we did the bus operation, and the next cycle is going to get a response. All we really need to do now is tell it we're done. We're done with the address part of the instruction. And at this point, the switch over to whatever the operation part is. And that should get us to the next instruction. Ooh, it got us a lot more than the next instruction. It got us quite a bit further. So let's just go over what worked, okay? So we read from A9, and then we jumped to the flags verification subroutine, and we got as far as 157, which I think means we actually exited the flags verification routine. 157. Right. That's the RTS. We came back from the flags verification. And now we did load A absolute, which is AD. And we failed on that. We failed on that because it's not an instruction we know how to implement, which means that we successfully implemented instruction A5. So you know what to do. We go over what we did. So we added it to the case. We added the 0-page addressing mode. Those are just changes in the Vivado project. Opcode A5, load a 0-page. Push, and the whole world can see. Woohoo. Okay, so we are at instruction AD. Instruction AD is, not here it is, load A absolute. And this is where this becomes really, really interesting in the power it gives us. Because what we need to do in order to implement this function is say AD begin, handle ADDR absolute, handle op LDA, and we are done. Since we've already implemented handle op LDA and we've already implemented handle ADDR absolute, that is all we need to do in order to implement this new instruction. We are at 158, which is the next, no. Okay, that did not work. Let's see why. Did I recompile? I did recompile. So let's go to the sync flag. We read from 310, which is this. We read the response data, it was AD. And then the instruction counter went ADDR1, ADDR2, ADDR3, ADDR4. op1 fetch. But it says the address bus expected 6D21 and received 0313. So we have a bug in the absolute addressing code. Let's see that. 6D21 ABS. So with advanced PC, we output the PC, and then we load the ADL from the data latch and put that into the ADL source, and we load it into the latch, and we advance the PC again. Okay, let's single step that. ADDR1. So we go back to ADDR1. We read from the PC. The PC is 0311, and we indeed read from 0311, and we read it here, which is ADDR2. Okay. Right. We advance the PC, we don't read. And then we read from the PC, so 0312. 0312. So far, so good. And DL at this point has 21 from 0311. So DL has 21 on ADDR2, but we don't do anything with it. We don't do anything with it because we're busy outputting the PC. So we postpone that. And on ADDR3, we're actually fetching DL, which is still 21. And we're doing what we expect with it. So we're putting it on address bus low, and we are loading it into request address low. Okay, we're not outputting a request, but we did update the latch for the address bus. So that's address bus ADDR3. On ADDR4, we got the reply to this read from 0312. So DL now contains 6D, which is what it should. And now what are we doing with it? On ADDR4, we're saying ADH source is this, control signals is this, and we completely forgot to say that bus rec valid is 1. Completely forgot to actually read the address. We spent all this time loading the address bus with the correct request, and we forgot to turn on the flag that says, but do the actual read. Okay, let's see if that breaks any previous code, because it might. Like I said, it did. Cycle 62. On cycle 62, we were in the middle of a jump. So let's see how our jump is implemented. Our jump says, if we are in the process of loading a value to the latches, load it also into the program counter. But at no point are we saying that we should cancel the read? Okay, so in order for this to work, we need to change the semantics a little. So let's look at the ADDR we did for 0 page. And what we're doing is we're not actually performing the read. If we're not actually performing the read here, we just added another cycle to the command. In LDA, in op1, okay, we'll handle that not nicely, but right now that's the best we can do. So what we'll do is we'll add a reg, which is a wire that says ADDR mode ADDR load value. So that's a single bit. And when we set the defaults for everyone, we'll set it to 0. ADDR load value is set to 0 by default. And now for when we do ADDR processing, the last fetch, the one that fetches the actual value we need to work on, will set ADDR load value to 1. So that's for 0 page, and for immediate, it's here. Actually, for immediate, it's a bit too late by now, but it doesn't matter. And for absolute value, it's here. And now, when we do jump, okay, let me explain what the problem is. When you look at the jump instruction, the data sheet treats it like it's a standard absolute mode instruction, right? Okay, it's absolute mode, just fetch the address and reset. But it doesn't behave like a standard absolute mode instruction, because if you're doing LDA absolute, you load the value, you use the 2 cycles to load the low and the high byte of the address you want to use, and then you do another fetch of the actual address. But for jump, you don't do that last fetch. You just put it into the program counter and use that. Now, since I didn't want to implement jump 3 times for the 3 addressing modes, I wanted to use the standard addressing modes. What I did for jump is I did not, if you look at the other instructions, for example, if you look at load A, for example, which is the only normal instruction here, it starts with, don't go into this loop if we're in the address fetch part of the instruction decode. Now for jump, what you'll notice is that we're still asking if we're in the address part of the instruction decode, but we are doing some handling. So for jump, we're doing some handling while the address decode takes place. And this handling overrides parts of the what we're saying essentially is if we're loading into the latches on the outputs of the address bus, also load into the program counter. So anything loaded into the latches also gets loaded into the program counter. But what we also need to do is prevent it from fetching the actual value from this address. And for that, we added the new control signal. So what we can do now is say, if ADDR load value, then bus rec valid is 0. So override what the address decode did. If the address decode said this is the fetching of the actual value, tell it no, it isn't. Forget about it. And this should get us to work for both normal opcodes and jump. It's not Lua, it's a System Verilog. It's a HDL, hardware description language. It looks like software, but it isn't. Essentially, the synthesizer sort of squashes, inlines everything, squashes all the different code paths, and then takes the last assignment under each situation. And we're back at 115, which we thought we were done with. And the problem is it expects A9, but received 030D. Because we started the next instruction. Because here we did not have a valid signal for some reason. Let's see why not. So we were in ADDR2. And in ADDR2 of 0 page, we are setting valid. Did I remove it? I think I removed it. We were at ADDR on line 55. Yep, for some reason I removed it. Let's put it back. Okay. This is what's called problem is between the monitor and the back of the seat. Okay, we actually passed 206 is a set carry instruction. So we actually managed to implement the next load A instruction. Let's just commit that before we make another stupid mistake. So we added the signal and we added load LDA absolute opcode AD. And pretty much that's it. Opcode AD LDA absolute. Okay, next instruction is a direct flags manipulation instruction. So set carry. Here it is. Says put 1 in the carry, and in the flags it just said 1 where the carry is, which is, kind of understandable. So let's see how that is implemented. When we look at the processor flags, so they are here, we have the carry 0, interrupt mask, decimal, break, overflow, and negative. And it can get data from the data bus, but also it can do processing of the data bus and ask whether all the bits are 0. And also, it has inputs from instruction register bit 5 and the ALU carry and the ALU overflow. So right now we won't need the ALU, but we will need So what we need essentially is to set the, right now we're on the carry, right? We're on set carry. So we need to set the carry to 1, which means we need to generate a 1 on the data bus. But that's not how we're going to do this. Now you'll notice that the carry has 3 control signals. So it says take it from the data bus bit 0. It says carry from instruction register bit 5 and carry from ALU carry. So ALU carry is pretty obvious, and data bus 0 just reflects that the carry is the rightmost bit, which means that when we push it to the stack or read it from the stack, it will be in bit 0, and this way we can copy it. So those two are pretty obvious. Instruction register 5 seems kind of strange, right? Instruction register is this register, and it keeps a copy of the opcode we're currently executing. So why would instruction register 5 be useful? If we look at the concise opcodes table, so this contains all the opcodes according to their order according to the machine language order. So this is 00, this is 01, this is 04, etc. And now let's look at the instructions that explicitly set the processor flags. So we have, we are currently executing set carry, which is 3-8. 3-8 set carry, but also 1-8 clear carry, and 5-8 clear interrupt, and 7-8 set interrupt, and 9-8 is something else, and B8 is clear overflow, which we'll skip right now, and then D8 is clear decimal, and F8 is set decimal. Why are those important? Those are important because aside from, so what we have is essentially 2 bits. Let's put that in this annoying flickering. Okay, so we're in hexadecimal. Let's look at them. Clear carry is 1-8. Again with the annoying flickering. Clear carry is 1-8. Set carry is 3. No, let's do that. Clear carry is 1-8. Clear interrupt is 5-8. Clear decimal is D8. And we had one more. Set decimal, clear decimal, set interrupt, clear interrupt, set carry, clear. No, that's it. And conversely, set carry is 3-8. Set interrupt is 7-8. And set decimal is F8. So clear carry, set carry, clear decimal, set decimal, clear overflow, clear decimal, set decimal, and clear interrupt, set interrupt. What you'll notice is that the difference 1-8, 3-8, the difference between the set and the clear is always bit 5. So if bit 5 is set, this is a set. If bit 5 is clear, this is a clear. Which means that what we can do is we can tell the flags register to copy bit 5 of the instruction register into the flag, and that will do the correct thing. So We were at, so let's do all of them while we're here, right? Now you'll notice I skipped one. I skipped clear overflow. Clear overflow, column 8. Clear overflow has bit 5 set, which is kind of annoying because why? But we'll handle it differently. No choice on the matter. Okay, so we had, let's do it like this. We had 8-bit literal in hexadecimal 1/8. We'd want to do handle op a set flag, and then 3/8, 5/8, 7/8, F8, and D8. So they all just called the same instruction, the same handler, and the bits of the instruction register are what sets them apart. Let's just place everyone in place. And we are at the ops section. Function handle op set flag. So what we want to do is this. New instruction, only one cycle, that's why it goes like this. We want control signals. So just a moment with that. We want, yeah, okay. So we want case, and we're looking at instruction register, but we're not looking at all the bits of instruction register because we want to save on logic. We only care about bits 7 and 6. Otherwise, we wouldn't have gotten here. So we're looking at instruction register bits 7 and 6. And then we're saying this is a 2-bit binary number. 00 is a CTL, and now we want for 0 is for the carry, right? So we want IR5 to carry. To carry. And then 0, 1, and 1, 1 are interrupt and decimal, I think. Other way around. Interrupt and decimal. So that should load the carry and clear the carry all in one go. Let's see if that actually works. I did something wrong, so let's elaborate, which will give us a better error message. Line 401. Right. And we're up to line 222. Which means into the clear overflow. Now, clear overflow, unfortunately, the designers of the 6502 broke their own pattern. I don't know why. So I know why we have a clear overflow and not a set overflow, because it has to do with an external signal called set overflow, which was envisioned to allow very tight reactions to external events. But I think it was only ever used in the Commodore floppy drive, in the Commodore 1541, and nowhere else. So that's why they had a clear overflow and not set overflow. But why they placed clear overflow with instruction register bit 5 set is beyond me. I have no idea why. Maybe transfer YA. I don't know. I have no idea why they did that. But it means we need to break our pattern. Which means that for instruction B8, begin handle op CLV. And then we duplicate this. And now we have a bit of a problem, because in order to clear the overflow, the control signals we got for the overflow are: take it from the data bus bit 6, take it from the ALU overflow, or set it to 1. We don't have set it to 0. Also, you'll notice that the data bus doesn't have any bit generation. However, while here the special bus doesn't have any bit generation, in our implementation it actually does have them. It could help to not duplicate. Everybody can read it like this, right? SB inputs, and you see that we do have an input that is all zeros. So I can set the special bus to all zeros, which I can do with, it's not like I remember, right? SBSRC, OSB, obviously. So SB source is CTL OSB. And then another thing I can do is the special bus can actually feed the data bus. So DB source, and it's called SBDB. And this will get me zeros into the data bus, which means that now I can also do DB something, DB6 to overflow. So all of this in order to clear the overflow. Let's see if it worked. 232. Yep, we're next to we're up to the ALU operations. So let's commit this. So all of the sets and all of the clears and the actual implementation. All set and clear flags ops opcodes. Okay. In terms of the subjects I promised this video will be about, we're on to the next subject, which is ALU. Do you want to continue? Because we're up to an hour also, so we're kind of out of time unless we decide that we're not. So up to you. Do you want to continue? And now I'm talking to myself while I'm waiting for the latency for the question to reach you, and then for me to decide whether you're answering. And nobody says anything. Okay, that settles it. Thank you everyone for joining me. I'll try to find what it will be the interesting point to continue with the next time, because it may not be, the ALU may be interesting, but it may not be the ALU. We'll see. And thank you for joining.